Hi, everybody. Welcome to Math with ACE, focusing on statistics today. We are continuing our discussion on chi-square. We did a chi-square goodness of fit test where we had multiple categories of a particular proportion, wondering whether a distribution matched or not. This was a single group. For instance, we're wondering whether the distribution of M&Ms matches. That is a situation where you have like these proportions match this value. Then we have other types of chi-square tests where we talk about tests for association. And there's two names for association that are typically used. One is independence, and one is homogeneity. Both of these calculate the test statistic the same way. They calculate expected values the same way. They use the same degrees of freedom. The difference is their null and alternative hypothesis and conclusion, and the data that is given to you. So you have to read the problem to determine if you're talking about independence or not. And independence, chi-squared, null, and alternative hypotheses are that the two things are independent or they're not independent. But we don't just say independent or not independent. We say that the two items that we're talking about, like salary and work experience, are independent or not independent. Hours that you work and the type of volunteer that you are independent or not independent. But these are always written in words. And again, you have a two-way table for these two. But when you're trying to talk about whether you have independence or homogeneity, what is a situation that would be independence? So independence is typically two groups within a particular population, where homogeneity is one variable across multiple populations. So this is typically two groups in a particular population. And homogeneity is where you have multiple across, you have a variable across multiple populations. Like the distribution of smoking is the same in two different, well, more than two different groups, like in these different cities or something like that. The null and alternative hypotheses for homogeneity is stating that the distributions are the same across these groups, and the alternative is that they are not the same. So in that situation, you are always giving context. And both of these hypotheses are not enough to just say independent, not independent, and distributions are the same, distributions are not the same. You need to talk about what is independent, what is not independent, what distributions are the same, what distributions are not the same. So context is always needs to be included and is important here. When you are calculating expected counts, just like with the other chi-square goodness of fit, your expected counts need to be at least 5 for that large condition. But the way that you do this, since you're in a two-way table, is you're multiplying the row total times the column total, dividing by the overall total. For example, if I have some sort of distribution where this is a total here, this is a total here, and maybe you have 1,000 individuals and there were 400 here and 100 here. Regardless, so if I was dealing with trying to figure out the expected count for this cell, I would multiply 400 times 100 and then divide that by the overall 1,000. So 400 times 100 divided by 1,000. And the beautiful thing about technology is that STAP will actually calculate your expected values for you, but it's good to know how they're calculated. So if I moved over to the next cell here, I'm using the same row total, but I'm using a different column total. And same thing here, same row total, different column total, and then you move down. So you would use 400 for each of those 3 different columns, and you would use 100 for each of those 3 different rows. Actually, 400 for those 3 different cells in that row and 100 for each of the cells in that column. That's how you get your expected counts. The chi-square test statistic is calculated exactly the same way. It's just that you're doing it for each cell. So you would take the observed minus expected squared over expected for cell 1, then this next cell here, then here, and 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 add all of those up. All of those contribute to your chi-square test statistic. The difference here is that I need to know what the degrees of freedom are in order to calculate my probability. And the degrees of freedom is found by taking the number of rows minus 1 times the number of columns minus 1. So in this case, there were 3 rows and there were 3 columns. So 2 times 2 would give me a degrees of freedom of 4 in this situation above, in this example, where I had this is column 1, column 2, column 3, row 1, row 2, row 3 in my example without numbers. So degrees of freedom, how many rows do you have? How many columns do you have? Subtract 1 from each of those and multiply. Then your conclusion is based on the p-value and your probability of calculations, same as with chi-squared, all of those things. So the conditions are the same as chi-square. The difference is how you calculate expected value and your degrees of freedom and the way that you set up your null and your alternative hypothesis. So let's get into some practice examples.